Hello, so welcome back to the channel. So in the first class, what have we learned? We have learned the definition of groups. We have also seen the three examples in the last video. Okay, the first one was the first example that we have considered was the set of integers with the operation being addition. The second example that we have considered was the set of non-zero real numbers with the operation being multiplication. And the third set, okay, that we have considered was this set Zn with the operation being addition modulo. Okay, so today we'll still be doing some more examples of groups, which will be really helpful for you if you have to master group theory, and also it is important for the course as well. Okay, so let's see. Okay, example number 4. Okay, the example number 4. Okay, so all right, so now let us do example number 4. Example number 4 is something that you may have studied again in the third semester. Okay, but I'll just write it anyway. Okay, so I hope you are familiar with matrices that you have also done in the first semester. So with matrices, you can add as well as multiply. Okay, but let us form a group with multiplication. Okay, so let's see. Okay, so this is a standard notation. Okay, G, L, N, R. Okay, this R stands for real numbers. This one stands for linear. Okay, and G just to say that it is a linear group. Okay, N it is the order of a matrix. Okay, square matrix. So what is this set? Set of n by n square matrices okay, with the determinant on equal 0, with determinant on equal to 0. Okay, so over here the operation will be multiplication. Okay, okay, so over here n, it can take any natural number. The value of n can be equal to 1, it can be equal to 2, it can be equal to 3, okay, and so on. It can be any natural number. So let us see. Okay, let us put the value n equal to. Let us see what are we getting. Okay, so I will put the value n equal to 2. Okay, if you put n equal to 2, so you will have G L2 R. Okay, so the operation is multiplication, so you will have something like this. It is A, the set, if you have to write it down, it will be A, matrix A, where A is a 2 by 2 real matrix. Okay, determinant A on equal to 0. Okay, so why do we need this determinant A on equal to 0? Okay, because if you remember, if we have to form a group, the elements have to be invertible. Okay, if you remember from the first semester and also from class 12, if A is a matrix, the inverse of A is given by this formula: 1 by determinant A adjoin A. Okay, so over here you can never divide by 0. Okay, so A inverse exists if determinant A on equal to 0. Okay, so that is why we need this determinant A on equal to 0, so that we can have an inverse for A. Okay, so how does A look like? Okay, A can take this form. So A, B, C, D. Okay, where so any element of the matrix, or I mean of the set GL2R will take this form: A equal A, B, C, D, where determinant A unequal to 0. Okay, determinant A, it's equal to AD minus BC. Okay, A, B, C, D, because it is a real matrix, they will be real numbers. Okay, so any element A will have this form. Okay, so always remember this. Okay, why I am doing this example, okay, you will need it for this semester. Okay, so again, okay, we can easily verify that this one is a group, but again, that is not required in this semester. But I just want you to know, to be familiar with the identity element as well as the inverse of an element. Okay, so let's see. If the group is GL2R, the identity element okay, spell the identity element. Okay, we usually denote it by E. Okay, so I will write it as E. Okay, over here will be 1 0 0 1. Okay, the identity element, okay, it's nothing but the identity element of the matrix, but always remember this is with respect to multiplication. Okay, if it is with respect to addition, you may have another identity element. Okay, but for this particular group where the operation is multiplication, the identity element is E equal 1 0 0 1. So clearly E, it is a 2 by 2 matrix. Moreover, determinant E, AD minus BC, is equal to 1 or equal to 0. So that is why it belongs to the set, okay, that we have considered, that is GL2R. Okay, so the identity element is this one, 1 0 0 1. But over here we won't denote it by E. Okay, if you remember, the identity element, in this case we will denote this one by I, capital I. Okay, so always remember the identity element of GL2R, it is this 1 0 0 1. Okay, what about the inverse of A? The inverse of A, again, we have that formula. It is equal to 1 by determinant A. Okay, adjoin of A. Okay, so the inverse of any element A will have this form: 1 by determinant A, adjoin of A. Okay, so that I hope you are clear with that example, GL2R. Similarly, if n equal 3, identity element, the identity element, okay, the identity element, something is wrong. Okay, the identity element will be equal to, it will be a 3 by 3 square matrix now, 0 1 0 and 0 0 1. Okay, the inverse stays the same. A inverse equal 1 by determinant A, adjoin A. Okay, it's just that the identity element changes accordingly to the order. All right, so similarly, when n equal 4, n equal 5, even when n equal 1, okay, it will be a 1 by 1 matrix. Okay, I hope that is clear with GL2R. Okay, again, I repeat, the purpose of these examples is just for you to be familiar with the identity element and the inverse element. Okay, so now let's look at example number 5. Okay, example number 5, it will take some time to explain. Okay, but the name of the group is symmetric group. Symmetric group of degree n. Okay, so over here we usually denote it by Sn. Okay, so once you see Sn, it is symmetric group of degree n. Okay, again, n can be any number that you put. okay, natural number 1, 2, 3, 4, and so on. Okay, so let us see what is this group. Okay, how does an element of this group looks like? Okay, so for matrix, it looks like matrix. For real numbers, it looks like real numbers. Okay, but this one, symmetric group, there is no idea at all from the name. Okay, why is it called a symmetric group? Okay, and also in this semester, we won't be going into the details of symmetric group, but let us just have an idea of what the elements look like. Okay, because you will need it in this semester as well. Okay, so let's see. Okay, so if you put n, okay, n is the number of symbols. Okay, just remember that, number of symbols. Okay, by symbols, okay, it can be numbers or letters or anything. Okay, but usually we will use numbers. Okay, so we will use numbers. Again, okay, so since we are with group theory, okay, so we have just learned about the set. Okay, what is the operation? The operation over here is composition. Okay, so the set is Sn. Okay, I will explain how does it look like, and the operation is composition. Okay, so over here the set, how does it look like? How does an element of the set looks? How does it look like? Okay, so let's see. Okay, so I will explain this one with S6 maybe. Okay, with S6. Okay, so we will have 6 symbols. Okay, the 6 symbols. Okay, because we can use A, B, C, D, E, F, G, A, B, C, D, E, F, or I think it's better if we can use the numbers. Okay, because I think it will be better if we use the numbers 1, 2, 3, 4, 5, 6. Okay, there are 6 numbers. Okay, so if you are having S6, there will be 6 numbers, and similarly if it is S7, there will be 7 numbers, and so on. Okay, so just imagine this one as a set. This set 1, 2, 3, okay, 4, 5, 6, 5 and 6. Similarly, imagine another set 5, 6. Okay, so what is this set? What does it contain? Okay, just like I said, if the set is a set of matrices, it will contain matrices. But if the set is a symmetric group, it will contain bijections. Okay, what is a bijection? Okay, so the set will contain bijections. Okay, bijection, it is a 1, 1 onto function. Okay, so again, let us go back to this when there are 6 symbols. Okay, so there are different ways that you can have 1, 1 onto function. So if 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, and 6 goes to 6, this one is 1, 1 function. Okay, so this function, okay, this whole thing, it is an element of S6. Okay, but it is very difficult to write it in this way. Okay, we will try to simplify that one. Okay, but first let us again take a look at this. Again, okay, can we have another function? Of course we can. Okay, maybe suppose 1 goes to 2, 2 goes to 3. Okay, you can have it in any way. Okay, as long as it is a 1, 1 function. Okay, so what are we having? This one is one element. This whole thing is one element. This other thing is another element. But again, to write it in this way, it's too cumbersome. Okay, because you will have to draw the diagram every time. Okay, so what we do, okay, we are using notation that will simplify it. Okay, so let us take a look. How will we write this one in a short way? Okay, All right, so 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6. So I will write it in this way. Okay, first, okay, let us understand this. Okay, if I have 4, 5, 6, okay, if I have something like this, how will I read this one out? I will say 4 goes to 5, 4 goes to 5, 5 goes to 6, and 6 goes to 1. Okay, all right, so this, and over here I will say 7 goes to 8 and 8 goes to 7. Okay, if I have another one, maybe 4, 5, 6, 8, 9, okay, just a single thing like this, I will say 4 goes to 5, 5 goes to 6, 6 goes to 8, 8 goes to 9, and 9 goes to 4. Okay, I hope it is clear with how do we say these things. All right, so let us take a look at this one. Okay, so over here we are having 1 goes to 1. Okay, just take a look at that. At this, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, and 6 goes to 6. So that first element we can write it as 1 goes to 1. Okay, so we will have to close it because it goes to itself. 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6. Okay, so we can denote it in this way. All right, so what it does when we are using it like that, it simplifies this diagram. Okay, just by looking at this notation, okay, you can clearly see the function. Okay, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 6. Okay, and what about this? Okay, what about the second example? Let's see. 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay, how will I write it down? 1 goes to, okay, maybe I will do it in the same page itself. Okay, I will use a different colored pen. Okay, if you have to write this one down, okay, you will write, so 1 goes to 2, 1 goes to 2, 2 goes to 3, 2 goes to 3, so that's why I'm writing 2 goes to 3, and 3 goes to 1. Okay, 3 goes to 1, so you will have to close it. Over here we are having another 4, 4, it goes to the number 4. Okay, so we'll close it. 5 goes to 5, 5 goes to 5, 5 goes to 5, and 6 goes to 6. Okay, so if you have to write it down, you will have to write like this: 1, 2, 3 together, 4, 5, 6 separately. Okay, so that second element you can write it down: 1, 2, 3, 4, 5, 6. Okay, so again, okay, just to be more clear, okay, let us try to represent this one in that form. Okay, just draw a 1, 1 onto function from the set. Okay, maybe 1 goes to 3, 2 goes to 4, 3 goes to 5, 4 goes to 2, 5 goes to 1, and 6 goes to 6. Okay, how will we represent this one in that easy way? Okay, so this is how we will do it. Okay, so 1 goes to 3. Start with the number 1. Always start with the smallest whenever you can. 1 goes to 3. 1 goes to 3. So over here now we are having the number 3. So 1 and this 3 have been used. Okay, now it starts with 3. So if it starts with 3, you go again to the set A. Look at 3. 3 goes to 5. 3 from set A goes to set B, 5. Okay, so now we are having this number 5. Again, we will go to the set A with number 5. 5 goes to, okay, this one, it shows to 1. If it shows to 1, so we will have to close it. 5 goes to 1. Okay, so we have used the symbols 1, 3, and 5. Okay, now let us take a look at 2. again because we have already closed the cycle, so 2 goes to 4. Okay, 4, again we'll start with 4 from set A. 4 goes to 2, 4 goes to 2, so we'll have to close it. Okay, so 1, 3, 5, 2 and 4 have been used. The only thing that is left is 6. 6 goes to 6. Okay, so we can write it in this way. Alright, 1, 3, 5, 2, 4, 6. Okay, so let's see something more. Okay, so that is how we can convert that diagram, that 1, 1, 1, 2 function into a better looking symbol. Okay, that will simplify things. Okay, but just to be more clear, let us try to do the reverse. Okay, suppose you are having 2, 4, 5, 1, 3, 2. Okay, suppose you are having this one. Okay, so sorry, 1, 3, 6. Okay, so let's have this. Okay, if we have to do it, if we have to draw the diagram for this, we will again have 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 6 in set B. Okay, so just take a look. 2 goes to 4, 2 goes to 4, 4 goes to 5, 4 goes to 5, and 5 goes to 2, 5 goes to 2. And then we are having this one, 1 goes to 3, 1 goes to 3, 3 goes to 6, 3 goes to 6, and 6 goes to 1, 6 goes to 1. Okay, so this is how we can convert. Okay, but this one, it is a diagrammatic representation, and this one, it's better, it's more concise, so we will be using this notation. Okay, whenever you are using this notation, okay, it is called a cycle notation of the elements of Sn. Okay, over here it will be S6. Okay, so we are using cycle. Okay, so over here we are having 2 cycles. Okay, also the elements do not repeat. 1 is not present in the first cycle, 3 is not present. Okay, so over here we are having disjoint cycles. Okay, sometimes the cycles can be disjoint, or sometimes they can not be disjoint. Okay, but we can always express anything in the form of disjoint cycles. Okay, but again, we won't do too much the details with that. Okay, so let us be more familiar with the notation. Okay, so when you are having something like this, okay, 4, 5 and 6, these elements, okay, they go to themselves. 4 goes to 4, 4 goes to itself, 5 goes to itself, 6 goes to itself. Okay, so it is best if we can even simplify further the notation. So instead of writing in this way, all the things that occur by themselves, we will not represent them. Okay, so once you see something like this, you can easily tell that 4 goes to 4, 5 goes to 5, 6 goes to 6. Even the numbers that are not present goes to themselves. 7 goes to 7, 8 goes to 8, 9 goes to 9. Okay, so that is how we will say. Okay, similarly, okay, to be more familiar, 1, 2, 3, 4, 5. Okay, suppose you are having like this. So you can see the number 6, it is not written. The number 6, it is not written. So that is why you can say 6 goes to 6. 1 goes to 2, 2 goes to 3, 3 goes to 1, 4 goes to 5, 5 goes to 4. But the number 6, since it is not present, it means that 6 goes to 6. Similarly, 7 goes to 7, in case we need the number 7, and also 8. Okay, again, just to be more clear, we can even have something like this. 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. The number 5, it is not present, so we can say 5 goes to 5, and also 6 goes to 6, and also the other numbers. Okay, so that is how we will do it. Okay, so over here again, okay, we won't be going to the details of Sn, okay, but we really need this example. Okay, you will see why, okay, once we start with the course. Again, I repeat, this is just a revision for 1 week. It will be just a revision of the things that maybe you have done in the first semester, okay, or the things that we will really need, okay, but not the details. Okay, so let's see. So Sn, okay, you will have cycles, okay, and over here the operation, it is operation, okay, you have all possible cycles with the operation being composition of cycles, okay, because cycles are nothing but functions, one on two functions, so that is why the operation, it is composition. Okay, how many elements are there in Sn? In Sn, okay, this one you should remember. Okay, again, I won't go into the details, but you really need it. In Sn, there are n factorial elements. Okay, so in S6 there will be 6 factorial elements. Okay, that is huge number. In S3 there are 3 factorial elements. Okay, so let's see. Okay, so again, let us come back to this S6. Okay, so we have learned that the elements of S6 can be expressed as disjoint cycles. Okay, the elements can be expressed as disjoint cycles, but we have not learned how to compose 2 cycles. Okay, we also haven't figured out what the identity of this is, and also what the inverse element looks like. Okay, so let's see. Okay, let us just consider. Okay, so what will there be in S6? In S6 there will be all possible cycles. Okay, 1 2 3, as long as you are using not more than 6 symbols. Okay, so this is one element. Okay, so many elements, 6 factorial elements, just imagine that. Even this one, it is an element in S6, even though 6 symbols are not present. Okay, 1 goes to 2, 2 goes to 1, but again I repeat, 3 goes to 3, 4 goes to 4, 5 goes to 5, and 6 goes to 6. So even though not 6 symbols are present over here, but they are hidden. Okay, so similarly, okay, you can have something like this. Okay, so many different ways. Okay, even 1 2 4 5 and so on. Okay, so many elements up to 6 factorial. Okay, but now we will learn first what is the identity. Okay, maybe it's best, how do we compose? How to compose 2 elements of Sn? How do we compose 2 functions? Okay, that is the question. Okay, but since now we are using cycles, it is easier. Okay, easier to see. Okay, so let's see. Okay, let me just add more pages. Okay, so maybe, okay, let us just take sigma. Sigma will be an element of Sn. Okay, let us take any element. Okay, maybe 1 to 4, 5, 6. Okay, so again I repeat over here, I am really stressing this point. There are only 5 numbers over here, 1 to 4, 5 and 6. The number 3 is not present, but it is hidden. 3 goes to 3. Okay, always remember that. 1 goes to 2, 2 goes to 4, 4 goes to 1, 5 goes to 6, and 6 goes to 5. Okay, maybe I will start with an easy example. Let's see. Okay, 5 6. Okay, this one will be easier. Okay, 1 to 4, 5 6. 1 goes to 2, 2 goes to 4, 4 goes to 5, 5 goes to 6, 6 goes to 1, and 3 goes to 3. Okay, tau. Okay, we are using Greek letters. Okay, but do not be confused. Okay, it is just a notation. We can even write this one by A, this one by B, it doesn't matter. Okay, but just to follow the standard way of doing it, we will be expressing the elements of Sn in terms of sigma, tau, or Greek letters. All right. Okay, so let's see. Okay, now let's take any element tau. Okay, maybe 2, 4, 1. Okay, so let's see. Again, over here, 2 goes to 4, 4 goes to 1, and 1 goes to 2, 3 goes to 3, 5 goes to 5, and 6 goes to 6. They are not hidden. Okay, suppose you have to find sigma tau. Okay. Okay, so suppose you have to find sigma tau. Okay, so let's write it down. Okay, this is how we operate two elements, compose. Okay, maybe I can even denote it with a dot. Okay, but most of the times we will even drop this dot. Okay, so sigma tau 1 2 4 5 6 and 2 4 1. Okay, so over here we are having a cycle, over here we are having a cycle, so over here also we will be having a cycle. This by itself, it is a disjoint cycle. This by itself, oh sorry, okay, forget what I said. Okay, so let's just try to find out how much is sigma tau. Okay, over here always remember we are in S6. Okay, if it is in S something else, okay, we have to be very careful. Okay, but over here we are in S. Okay, even though if it is not written in S6, okay, just see the letters 1 2 4 5 6. Okay, you can tell, okay, that it will be in S6. So let's see. Okay, so how will we do it? Just see how many cycles do we have. 1 2. Okay, I will say that this one is the first cycle, even though we are writing it on the right towards the end. Okay, but I will say that this one is the first cycle, and I will say that this one is second cycle. Again, there is a reason why we are saying it in this way. There is a reason why I am saying that the one I've written at the end is the first cycle, and why I've written why the one I've written in the beginning is the second cycle. Okay, but if we have time, okay, we can always I will try to clarify that as well. Okay, but there is a reason. Okay, so let's see. First, second, okay, we will have some result over here. Okay, so always remember, if you have two cycles, there will be two arrows. Okay, two arrows. The first arrow is from the first cycle, and the second arrow is from the second cycle. Okay, the starting point, it will always be the smallest number that is present in the two cycles. Okay, so the smallest number, it is 1. Okay, so we'll start with the number 1. Okay, 1. From the first cycle, okay, since the first arrow is from the first cycle, okay, so I will see. Okay, so over here we have started with 1. Okay, so that is why over here also I will write number 1. Okay, but we don't know where it goes to. Okay, so now let's look. The first arrow is from the first cycle. From the first cycle, 1, where does it go to? 1 goes to 2. Okay, so that is why over here I will say it goes to 2. Okay, so now we are in the second cycle. Okay, 2. Now it is starting from 2 in the second cycle. In the second cycle, 2 goes to 4. Okay, 2 goes to 4. Alright, so from the first cycle, 1 goes to 2. In the second cycle, 2 goes to 4. Okay, so that is why over here 1 goes to 4. The overall result is 1 goes to 4. Alright, so 1 goes to 4. Okay, so we won't close it yet. Why we won't close it yet? Because 1 is going to a different number. If it goes to the same number, then we will close it. Okay, so now over here we are having the number 4. So now we will start with 4. Again, first cycle, second cycle. Let's see. In the first cycle, 4 goes to 1. Okay, in the first cycle, okay, maybe I'll use a different pen. 4 goes to 1 in the first cycle. 4 goes to 1. And in the second cycle, 1 goes to 2. Okay, 1 goes to 2. So 1 goes to 4. And this one, the overall effect, 4 goes to 2. Okay, so 4 goes to 2. Okay, so now we will start with 2. Okay, I will start with 2. Again, first cycle, second cycle. Let's see. 2 goes to 4. Okay, so 2 goes to 4. And 4 goes to 5. In the second cycle, 4 goes to 5. So 2 goes to 5. Okay, so 2 goes to 5. Okay, so now we'll start with 5. First cycle, second cycle. 5, there is no 5 in the first cycle, but always remember it is hidden, so 5 goes to 5 in the first cycle. Okay, 5 goes to 5 in the first cycle. What about in the second cycle? In the second cycle, 5 goes to 6. So that's why we are having 5 goes to 6. 5 goes to 6. Okay, so now we'll start with 6. This is a tedious process. Okay, but once you can get the hang of it, okay, you will be faster. 6. In the first cycle, 6, it is not present, so it goes to 6. In the second cycle, 6 goes to 1. Okay, so 6 goes to 1. Okay, so now we have to be, the overall effect is 6 goes to 1. So what I will write down over here, okay, I can write it in this way. Okay, but okay, I should be careful. Okay, because they should be disjoint. Okay, if I write 1 and 1 over here, okay, it's like the same number is occurring 2 times. I cannot do that, so that is why I will close it. 1, 4, 2, 5, 6. Okay, but the number 3, it still hasn't occurred. Okay, so we will have to take care of that separately. Let's see. 3, first cycle, second cycle. 3, in the first cycle, it goes to 3. In the second cycle, it goes to 3 again. Okay, 3 goes to 3, it goes to 3. Okay, so we can write it in this way. 3 goes to 3. Okay, so all the 6 symbols have been used, but again 3 goes to 3, so it can be deleted. Okay, we can just have this result 1, 4, 2, 5, 6. Okay, so I think this is enough for now. I will send some more examples how to compose cycles. Okay, maybe through a text document. Okay, I will try to do that. Okay, and also in the next time we will try to see what will be the identity element of this symmetric group and what will be the inverse of an element in this symmetric group. Just to summarize what we have done today, okay, we have seen an example, the group of invertible matrices GL2R, GL3R, in general GL and R, and over here right now what we have just done, we have learned about the symmetric group Sn, where n is a natural number. And also we have learned that the elements in Sn, they are cycles, and we have also learned how to compose cycles. Okay, I think that is enough for now. Okay, bye.